तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we looked at the complementary slackness conditions, and we also said that the simplex method also gives the solution to the dual at the optimum. We also wanted to find out how the Cj minus Zj's in the intermediate iterations represent something, or do they represent anything. To consider that further, we will take the familiar example and try to interpret the Cj minus Zj's corresponding to the intermediate iterations of the simplex algorithm. So, the example is maximize six x1 plus 5x2 subject to x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. Very quickly performing the simplex iterations, we get x1, x2, x3, x4, right hand side. We start with x3, x4, 1, 1, 1, 0, 5, 3, 2, 0, 1, 12, 6, 5, 0, 0. Now variable x1 with the largest positive Cj minus Zj enters. Corresponding theta values are 5 and 4. So 4 is the minimum theta. So variable x1 enters to get x3, x1 Cj minus Zj. Dividing by the pivot element, we would get 1, 2 by 3, 0, 1 by 3, 4. This minus this would give us 0, 1 by 3, 1, minus 1 by 3, 1, z equal to 24, 0, 0. 6 into 2 by 3 is 4, 5 minus 4 is 1, 6 into 1 by 3 is 2, we get minus 2 here. So variable x2 enters the basis. So this is 1 divided by 3 is 3, 4 divided by 2 by 3 is 6, this leaves pivot element. So x2 replaces x3 in the basis. So the final table will look like this. Dividing by the pivot element, we get 0, 1, 3, minus 1, 3. This minus 2 by 3 times this will give 1, 0, minus 2, 1 by 3 plus 2 by 3, which is 1, 4 minus 2 by 3 into 3 is 2, Cj minus Zj values are 5 into 3, 15, minus 12, 3, we get a minus 3, minus 5 and 6 would give us a minus 1 and 27. In the last lecture we saw that this minus 3 and minus 1 when multiplied with a minus 1 again would give us 3 and 1, which are the values of the dual at the optimum. We also said that x1, x2, x3, x4, now x3, x4 are our u1 and u2, which are the primal slack variables. So we replace them by u1 and u2 here, and x3 also becomes u1. From the complementary slackness we understand that there is a relationship between x and v and y and u. So the whatever comes under x we can write it as v1 and v2. Primal decision variables have a relationship with the dual slack. Primal slack have relationship with the dual decision variables. So we say that with, of course with a minus sign. So y1 equal to minus 3, y2 equal to minus 1 represents the value here, y1 equal to plus 3, y2 equal to plus 1 represents the values of the dual at the optimum. Now let us look at an intermediate iteration here. And in this intermediate iteration, solution to the primal is x1 equal to 4, u1 equal to 1. Now let us apply the complementary slackness and see what happens. Now when we apply complementary slackness to this, x1 basic indicates v1 equal to 0, u1 basic indicates y1 equal to 0 and non-basic. Now here x2 and u2 are non-basic, indicating that v2 and y2 are basic for the equivalent solution to the dual if we apply complementary slackness condition. Now rewriting the dual for this problem, dual is to minimize 5y1 plus 12y2 subject to y1 plus 3y2 minus v1 equal to 6, y2 plus 2y2 minus v2 equal to 5, y1, y2, v1, v2 greater than or equal to 0. Now when we apply complementary slackness to this, we have to solve for v2 and y2, which are the basic variables. So this solution will become 3y2 equal to 6, from which y2 equal to 2, and from here we have y2 minus v2 equal to 5, from which v2 equal to minus 3. So when we apply complementary slackness conditions to an intermediate iteration of the simplex algorithm and evaluate the corresponding dual as we have done here, the corresponding primal solution is u1 equal to 1, x1 equal to 4, z equal to 24. When we apply complementary slackness and solve, we get y2 equal to 2, v2 equal to minus 3, z or w equal to 5y1 plus 12y2, w is also equal to 24. Now let us go back to this intermediate iteration and see whether we have this solution reflected somewhere in the Cj minus Zj. If we go back, now we have y2 equal to 2, we realize this is y2. So the value here under the Cj minus Zj once again multiplied with a minus 1 gives us the value of y2. v2 equal to minus 3. Now y2 and so I have y2 equal to 3 from this, and I have y1 plus 2y2 minus v2. So 2y2 minus v2 equal to 5, so v2 is minus 1. Okay. So v2 is minus 1, v2 is here, which is shown under x2, and we realize the negative of this number is minus 1. So what we observe here is, if we take an intermediate iteration of the simplex algorithm, write the complementary slackness corresponding to that, and then evaluate a corresponding dual, we realize that the solution to that dual is also seen under the Cj minus Zj of the intermediate iteration. So, in some sense simplex satisfies complementary slackness conditions at every iteration of the algorithm, not only at the optimum. Now, we see some more interesting things happening. It satisfies the complementary slackness conditions, it gives an equivalent solution to the dual after the complementary slackness conditions are applied, and we get the same value of the objective function for the primal and dual respectively. We also realize that the dual is infeasible here because V2 is minus 1. We would want y1, y2, v1, v2 all greater than or equal to 0. Now, V2 is minus 1. Now, the infeasibility of the dual, which is V2 equal to minus 1, is now reflected in the corresponding non-optimality of the primal. You can see that V2 equal to minus 1 is actually represented as a C2 minus Z2 equal to plus 1, which enters the basis to get the next iteration. So, whichever dual variable is infeasible or whichever dual constraint is infeasible, after all V2 equal to minus 1 comes from the fact that y1 plus 2 y2 is not greater than or equal to 5. So, this V2 is nothing but the extent to which y1 plus 2 y2 is greater than 5, because the actual constraint is y1 plus 2 y2 greater than or equal to 5. So, if y1 plus 2 y2 is strictly greater than 5, then V1 will take a positive value. Now, in this case, because y1 plus 2 y2 is less than 5, V2 takes a negative value. So, V2 taking a negative value indicates that the second constraint is violated. So, a dual is infeasible when either the decision variables take negative value or the slack variables take negative value. Slack variable taking negative value represent the extent of not satisfying a particular constraint. So, the extent of infeasibility of the dual represents the extent of non-optimality of the primal. If the second dual constraint is violated by 1 unit, then it implies in the simplex algorithm that the corresponding decision variable, if this slack variable takes a negative value, the corresponding decision variable, which is non-basic because of the complementary slackness condition, will now try to enter the basis and will indicate the rate of increase of the objective function, which is 1, which is the same minus 1 which you see here. So, simplex not only satisfies the complementary slackness conditions at the optimum, at every iteration of the simplex algorithm the complementary slackness conditions are satisfied, and in every intermediate iteration a non-optimal iteration with respect to the primal is an infeasible solution to the dual, and the extent to which the entering variable in the intermediate iteration corresponds to the infeasible dual slack if a decision variable enters, or a dual decision variable if a slack variable enters, and the rate, the Cj minus Zj corresponding to the entering variable is actually the extent to which the dual is infeasible. So, non-optimality of the primal, which is represented by an intermediate iteration, represents infeasibility to the dual. So, now there is a different way of looking at this Cj minus Zj. So, what the simplex algorithm does is, remember that the right hand sides are always greater than or equal to 0, and the rule for the leaving variable will ensure that the right hand sides will never become negative. So, simplex as an algorithm will always have a primal solution which is basic feasible, it will not have an infeasible solution at all. Now, this represents the feasibility of the primal, this represents either the optimality of the primal or the feasibility of the dual. So, this indicates, the plus value here indicates that the corresponding dual is infeasible with a negative. So, what simplex tries to do is, it starts with a feasible primal and an infeasible dual. This would mean both x1, both v1 and v2 are negative. So it starts with a feasible primal, it has an infeasible dual, and it tries to make the dual feasible. The extent of infeasibility of the dual is given by the Cj minus Zj of the corresponding value. So it tries to take that variable which is least feasible by picking up this 6 here, which is nothing but the maximum rate at which I can increase the objective function for the primal. So in successive iterations it tries to make the dual feasible. Now here you have two dual variables that are infeasible, here you have one dual variable that is infeasible. So it tries to make the dual also feasible by applying complementary slackness. Now in the end, when both the primal and the dual are feasible, then the optimal is reached after applying the complementary slackness. So the optimality can be looked at in this way. Now we can go back and try to even interpret all the duality theorems. 1, you have a basic feasible solution here with an objective function value of 27 that is feasible to the primal. You also have a feasible solution to the dual with the same value of the objective function, therefore it is optimal to both primal and dual respectively. Now simplex as an algorithm is always feasible to the primal, it applies complementary slackness and tries to evaluate the corresponding dual in every iteration. The moment it finds that the corresponding dual is also feasible, then it is optimal. So simplex can be seen as an algorithm which actually solves both the primal and the dual, but it keeps a basic feasible solution to the primal and works towards getting a feasible solution to the dual, thereby making it optimal. Now simplex comes under a category of what are called primal algorithms. It is called a primal algorithm. A primal algorithm always has a feasible solution to the primal, satisfies complementary slackness or applies complementary slackness and terminates when the corresponding dual is feasible, indicating that both primal and dual are feasible and optimal. So in some sense we do not need to solve the dual at all. We now realize that when we solve the primal, we are automatically solving the dual, and we can always get the solution to the dual of the problem that we are solving from the final iteration. This is the primal that we have solved, solution to the primal is here, solution to the dual of this problem is here with y1 equal to 3, y2 equal to 1, z equal to 27. Okay, let us go back and see this. Now the optimum solution to the dual can be read from the optimum tableau of the primal in the simplex algorithm, and we need not solve the dual explicitly at all. Next. Now if we look at an intermediate iteration, whatever we have tried to show here is what is explained here. This solution is infeasible to the dual because variable v2 takes a negative value, which is here. You have to remember constantly that we need to multiply this with a minus 1. So this is actually the negative dual variable, not this. Now it just shows that this constraint is violated by the same quantity of 1 which is seen here. At the optimum, when complementary slackness conditions are applied, resultant solutions is feasible to the dual and hence optimal. Next. Simplex can be seen as one that evaluates basic feasible solutions to the primal, applies complementary slackness conditions and evaluates the corresponding dual, and when the primal basic feasible solution is non-optimal, as in an intermediate iteration, the dual will be infeasible, and as and when the dual becomes feasible, we get the optimal solution for both the primal as well as the dual. Yeah. We next look at what is called as a dual simplex algorithm and try to see another version of simplex which is quite interesting and different from the version that we have seen. we take an example, minimize 4x1 plus 7x2 subject to 2x1 plus 3x2 greater than or equal to 5, x1 plus 7x2 greater than or equal to 9, x1 x2 greater than or equal to 0. Now we add slack variables, because of the greater than or equal to we have negative slack, so we have minus x3 equal to 5, minus x4 equal to 9, x3 x4 greater than or equal to 0. Normally we would have added two artificial variables a1 and a2 to get the basic feasible solution, because x3 and x4 by themselves are not capable of giving us a starting basic feasible solution, because x3 equal to minus 5, x4 equal to minus 9 is infeasible. But now let us see what happens if we still start with x3 and x4. So let us go back. Now first thing we do is we convert this problem to a maximization problem. So we have x1, x2, x3, x4. We are not going to add artificial variables at all. So the problem becomes maximize minus 4x1 minus 7x2 0x3 0x4. We now still keep x3 and x4 as basic variables. Now we multiply this, because this is equal to 5, we multiply this with a minus 1 to get minus 2x1 minus 3x2 plus x3 equal to minus 5. So minus 2x1 minus 3x2 plus x3 plus 0x4 equal to minus 5, minus x1 minus 7x2 minus 1x1 minus 7x2 0 1x4 equal to minus 9. We have 0 and 0 here. Right now we have violated a very important assumption in simplex, that the right hand sides should be greater than or equal to 0. Now we have a solution which is not basic feasible, but has completely negative right hand side values. But let us look at Cj minus Zj. Now Cj minus Zj for this would give us a minus 4 here, minus 7 here, 0, 0. Because we have zeros here, they do not contribute at all, Cj minus Zj would simply become Cj, so we have this. Now because of the problem, we will then come back to what is peculiar about this problem, but we definitely observe that the optimality condition is satisfied. The optimality condition is satisfied, the feasibility condition is not satisfied. Or just extending whatever we had seen, the dual corresponding to the solution x3 equal to minus 5, x4 equal to minus 9 is feasible, because I have a completely negative Cj minus Zj, the dual is feasible. So we have a simplex iteration where the primal is infeasible but the dual is feasible. In all our earlier simplex versions, in any first iteration or intermediate iteration, the primal will be feasible, dual will be infeasible. Now we have exactly the opposite happening, the primal is infeasible, the dual is feasible. Now we can still work out simplex if we can maintain the feasibility of the dual and slowly make this feasible, then it will become optimal. In a normal simplex what we did was, we maintained this feasibility, we tried to bring the dual feasible and we got the optimal. Now here we can, if we can keep the dual feasible consistently and then make this one feasible, then it will become optimal. So let us do that. Now we cannot have an entering variable here, because all the variables are with a negative Cj minus Zj. So the first thing we need to do is we need to somehow make this feasible, which means we need a positive value or a non-negative value on the right hand side. So the most negative of these will leave first. So we first find out the leaving variable and leave out the variable with the most negative value of the right hand side. So this will leave. So we are trying to do some steps, some part of the simplex which is the opposite, and some part of the simplex which is common to the earlier one. So here we first find out the leaving variable. Now we need a variable that can enter and substitute this x4. To do that we compute a theta, but theta now comes in the row because we have to find out an entering variable next. To do that we do something very similar, take this value and divide here. So minus 4 divided by minus 1 is 4, minus 7 by minus 7 is 1, we have 0 and we do not do. So we can leave this because we always, these are the basic variables, so we want only one of the non-basic variables to enter. So you do not have to evaluate the theta for what are presently the basic variables. You will evaluate the theta only for the present non-basic variables. So these are the theta values. Now once again the smallest theta will enter, so we have this. Now what happens as a result of this? In this algorithm, the Cj minus Zj's will always be negative, and we need a negative pivot, because when we do the simplex iteration next, when we divide this by the pivot element, we will then get a positive value here. So in this case you would need a pivot that is negative, and this value will always be negative, so you will compute thetas only for negative values in the row corresponding to the leaving variable. If there is an element with a positive value in the row corresponding to the leaving variable, we will not compute the theta even if that is a non-basic variable. For example, if this had been a plus 1, we would not have computed this theta at all. Very similar to situations where we do not compute theta in the earlier version of the simplex. In the earlier version of the simplex, if that number is negative, you would not compute theta, or if that number is 0, you would not compute theta. Here, if that number is positive or 0, you will not compute theta. So you will not compute theta here because of this 0. In any case, this is a basic variable, so you will not do that. Now variable x2 enters and variable x4 leaves. I have x3, x2. Now this is minus 7, this is 0. So divide by the pivot element to get 1 by 7, 1, 0, minus 1 by 7, 9 by 7. We need a 0 here, so this plus 3 times this would give a 0, this plus 3 times this would give a 0, minus 2 plus 3 by 7 is minus 11 by 7, 0, 1, this plus 3 times this would give us minus 3 by 7, this plus 3 times this, minus 5 plus 27 by 7 is minus 8 by 7. So minus 8 by 7, 9 by 7. By 7, and we have z equal to minus 9 here. Now we need to find out Cj minus Zj. x3 and x2 are basic variables, so we get 0 here. This 0 into minus 11 by 7 plus minus 7 into 1 by 7 minus 1, minus 4 minus 1 is minus 3. Here I have a plus 1, so 0 minus plus 1 will give me minus 1. So once again I have Cj minus Zj is less than or equal to 0, the optimality condition is satisfied. How is it satisfied? That is because of the minimum theta rule that we followed to define the entering variable. So we make sure that the optimality condition is satisfied. Now the feasibility condition is not satisfied because this has a negative right hand side, so this has to go. Now we need to find out the entering variable corresponding to this leaving variable. Now we do this, we compute theta again, minus 3 divided by minus 11 by 7 is 21 by 11, minus 1 divided by minus 3 by 7 is 7 by 3, 21 by 11 is smaller than 7 by 3, So, variable x1 enters and this is the pivot. Remember that the pivot element has to be negative in this case. Only when the pivot element is negative, the right hand side will become non-negative in the next iteration. So, we continue with the simplex. The simplex iteration part of it is the same, it does not change, the row operations are all the same. So, we have x1, x2, x1 with a minus 4, x2 with a minus 7. So, dividing by the pivot element or multiply by minus 7 by 11, which is 1, 0, minus 7 by 11 plus 3 by 11. Now, this is 8 by 11. This minus 1 by 7 times this is 0. So, 1 by 7 minus this is 0, this is 1. This minus 1 by 7 times gives me plus 1 by 11, minus 1 by 7 minus 1 by 7 into 3 by 11. So, minus 1 by 7 minus 3 by 77 is minus 14 by 77, which is minus 2 by 11. 9 by 7 minus 1 by 7 into 8 by 11. So, 9 by 7 minus 8 by 77. So, 99 minus 8 is 91 by 77, which is 13 by 11. So, we get 13 by 11 here, and then the value here will be 32 plus 91 is 123 by 11 with a minus sign, 123 by 11. Now, Cj minus Zj values are all 0. So, Cj minus Zj is all 0. Now, this is plus 28 by 11 minus 7 by 11 is plus 21 by 11. So, 0 minus plus 21 by 11 is minus 21 by 11, minus 12 by 11 plus 14 by 11 is 2 by 11. So, 0 minus 2 by 11 is minus 2 by 11. Once again the Cj minus Zj values are negative, indicating that the optimality condition is satisfied. Now, we realize that the solution is feasible, feasibility condition is also satisfied, therefore, this is optimal. And you can also show that, for example, 21 by 11 into 5 plus 2 by 11 into 9 will also give us 123 by 11. 105 plus 18 will give 123. So, the optimal solution to the primal is x1 equal to 8 by 11, x2 equal to 13 by 11, z equal to plus 123 by 11. The minus comes because we have converted a minimization problem into a maximization problem by multiplying with the minus 1. Optimum solution to the dual will be y1 equal to 21 by 11, y2 equal to 2 by 11, w equal to 123 by 11. Now, this algorithm is called the dual simplex algorithm. Now, let us go back to this. Now, both x1 and x2 are feasible. So, right from the first iteration the optimality condition is satisfied, we do not have a leaving variable, the algorithm terminates to give us the optimum. Next, above algorithm is called the dual simplex algorithm. Now, what is special about the dual simplex algorithm? The dual simplex algorithm is very well suited when you have all greater than or equal to constraints. We are not unduly worried about the objective, but it is very well suited when you have a minimization problem with all positive coefficients here, so that the equivalent maximization will have all negatives and the first Cj minus Zj will have all negatives. So, it is very well suited for a minimization problem with all positive coefficients in the objective function and all constraints of the greater than or equal to type with a non-negative right hand side. The non-negative right hand side is granted when we formulate the problem. So, all greater than or equal to constraints with non-negative right hand side, minimization function, all non-negative or positive coefficients, this algorithm is very well suited. We do not need to introduce artificial variables at all, no need to do the big M method, we can still use the dual simplex and solve. Now the condition for dual simplex is we will have to have the Cj minus Zj's negative to begin with. This will be also negative, indicating infeasibility. We will retain the optimality condition by a careful choice of the entering variable and theta, by following a similar minimum theta rule. By making the pivot element negative, or by pivoting on a negative element corresponding to the leaving variable, we make the corresponding right hand side non-negative, so that we ensure that we are converting in every iteration, we are converting at least one negative value to a non-negative value. Once again, it is not absolutely necessary that within 2 iterations this has to converge. We may encounter a situation where, for example, here by doing one iteration we are making sure that we have a non-negative number here, but things can happen that this could be negative and then it could go on, but if the algorithm has a solution then it will terminate. Now the dual simplex algorithm, we have to make sure that the pivot element is negative. Only when the pivot is negative we can get a positive here, and therefore the theta is computed in such a way that it is computed only for those variables, non-basic variables, which have negative coefficients or completely negative coefficients in the leaving row, and then the minimum theta will ensure that the optimality condition is satisfied. Right. Feasibility condition is not satisfied by the starting solution. When the solution is feasible, we say that the optimum is reached. It is called dual simplex for a very specific reason. There are 2 ways of looking at it. So far we are used to having a maximization problem with less than equal to as our primal. Then we might be tempted to believe that the dual of the primal, the way we have defined, is a problem that fits into this structure, which is correct. The dual of the problem that we defined as primal right through fits into this structure, and we might be tempted to call this dual simplex because it can solve the dual of our primal, but that is not the real reason. The real reason is whatever problem you choose to solve, the moment you start the dual simplex algorithm, if you look at this carefully, the optimality condition being satisfied indicates that solution to the dual of the problem that you are solving is feasible. So right through the dual simplex algorithm you have a dual feasible solution, primal infeasible, and the moment primal becomes feasible it is optimum. It is called dual simplex because at every iteration of the simplex the dual of the problem that you are solving is feasible, whereas in the regular simplex, which you may now call as primal simplex, the problem that you are solving is feasible in all iterations, and the moment its dual becomes feasible it is optimal. So we need to understand that it is called dual simplex because at every iteration of the simplex algorithm the dual to the problem that you are solving is feasible, represented by the optimality condition being satisfied. Therefore it is called a dual simplex algorithm. This comes under the category of what are called dual algorithms. Now dual simplex is an example of a dual algorithm. A dual algorithm will have a feasible dual always, or dual to the problem that you are solving is always feasible, applies complementary slackness, and the moment primal becomes feasible it is optimal to both primal and dual. So the regular simplex, also called primal simplex, is a primal algorithm. Dual simplex is an example of a dual algorithm. Yes, now let us go to another type of problem. Now we have taken a problem which has mixed type of constraints. You have a greater than or equal to constraint, you have a less than or equal to constraint, you have all those, and more importantly you have an objective function, though it is maximized, it does not have all positive coefficients. So far we have not looked at a problem which had a negative coefficient in the objective function. We looked at it only after we converted it to a maximization problem, we could get negatives, but we never had a mixed set of objective function coefficients, we never had a mixed set of right hand sides. Now if we have a problem like this, then what do we do? 1. The simplest and the easiest thing to do is the second constraint, x1 plus x2 less than or equal to 3 is the kind of constraint that we want, because the slack variable plus x4 will automatically qualify to be a basic variable. The first constraint being a greater than or equal to would now give us a negative slack which would not qualify normally. We would have added an artificial variable a1 there, and it is easy to start the simplex table with a1 and x4, use the big M method and solve it. Now, after having learnt the dual simplex, which helps us to solve problems without introducing artificial variables, now can we apply dual simplex to this problem? Now right now we cannot apply dual simplex to this problem as it is, because when we write a minus x3 here and a plus x4 here, the combination x3 x4 has an infeasible right hand side, as you can see here. The right hand sides will be, I will have a x 1 0 0 1 with a minus 1 and 3. When we write the Cj minus Zj, we convert it, we have a maximization problem. If we start with x3 and x4, we have a minus 1 and 5. So we encounter a situation where neither the primal is feasible nor the dual is feasible. This 5 indicates that the dual is infeasible. A positive Cj minus Zj would indicate that this variable can enter, which means that the corresponding dual, when I apply complementary slackness, is infeasible. When we applied the dual simplex algorithm, we made sure that all these were less than or equal to 0 and the dual was feasible in all the iterations. Now we come to a situation where the dual is infeasible, but we can still do this. So let us go back and see. You can do two things. You can either leave this variable, treat this as a leaving variable first and then perform a dual simplex iteration, or you can enter this as your variable and perform a simplex iteration. You can do either. So what we are trying to show now is that we have a negative value for variable x3 as well as a positive value for Cj minus Zj, indicating that both the primal and the corresponding dual are infeasible. So you cannot entirely apply the simplex algorithm or entirely apply the dual simplex algorithm. If you want to solve this problem without artificial variables, you have to judiciously mix a simplex iteration and a dual simplex iteration and proceed till the optimum. We show that through this example. You can actually do a simplex iteration by entering variable x2 here with a 5, or you can do a dual simplex iteration by leaving out this. So we choose the simplex iteration. In fact, there is a general thumb rule that when both the simplex and dual simplex iterations are possible, the thumb rule is do the simplex iteration first. So we enter variable x2 with 5, and that now doing a simplex iteration for this you cannot have theta, because in a simplex iteration you would want the feasibility to be maintained. So you will not compute a theta for this, you will compute a theta only for this. You have a right hand side 3, you have x2 1, so the theta value is 3 and variable x4 will leave the basis. This is 3 instead of 2 and variable x4 will leave the basis. We do the next iteration. Next iteration is with x3 and x2. When we do a simplex iteration, you now get into a situation where your Cj minus Zj's are negative, which means the dual is feasible, but then the primal is infeasible because x3 now has a negative value. Now in this iteration you can do a dual simplex iteration because your optimality condition is satisfied and the feasibility condition is violated. So you can do a dual simplex iteration, which is the only thing possible. Simplex iteration is not possible here because you do not see an obvious entering variable, whereas you see an obvious leaving variable. So you do a dual simplex iteration by leaving out variable x3. That is what is written here. The primal is not feasible, but the dual is feasible. You can only do a dual simplex iteration with x3 as a leaving variable. And when we try to compute the theta, you will get 6 by 5 and 5 by 3. 6 by 5 being smaller, variable x1 will now enter. So you will do a dual simplex iteration with variable x1 replacing variable x3, and that is shown in the next iteration. Now you have x1 equal to 2, x2 equal to 1 with z equal to 3, which is your feasible solution to the primal, and the feasible solution to the dual will be y1 equal to 6 by 5, y2 equal to 7 by 5 and w equal to 3. Now you have a situation where your right hand sides are non-negative, primal is feasible, you have the optimality condition satisfied, so dual is feasible. You have now reached the optimum to both primal as well as dual. So the simplex method can also be used to solve situations where we can have mixed type of constraints. So when we have a mixed type of constraints and mixed coefficients in the objective function, as we saw in this example, you could have a positive and a negative here, you could have a greater than equal to constraint and a less than equal to constraint. When you have an equation, you might still be forced to use an artificial variable if necessary, because splitting the equation into two constraints complicates further because you are increasing the number of constraints. The effort will increase, so we would not choose to do that. If you have only inequalities and if you have a mixed type of constraints, you can still use a judicious mix of simplex and dual simplex iterations and solve the problem. The only assumption that we have made here is the problem has a solution and we got the optimal solution. But we could get into situations if, for example, a problem with mixed type of constraints and with positive and negative coefficients in the objective, if the problem is unbounded or infeasible, then we need a way to understand whether the problem is unbounded or infeasible. The usual conditions will still apply. For example, even when you mix a simplex and a dual simplex iteration, or even within a dual simplex iteration, you might get into a situation where I can find a leaving variable, I may not be able to get an entering variable. That can happen. Now that does not directly ensure unboundedness, whereas those things are very well defined in a simplex iteration. In a dual simplex iteration, if we get into a situation where I have a leaving variable and I do not have an entering variable, that can happen. Now such a thing would actually indicate infeasibility of the problem. Now we have to go back and define how we look at unboundedness and infeasibility with respect to the dual simplex, or we look at unboundedness and infeasibility with respect to applying simplex and dual simplex alternately, as in the case of problems with different types of constraints and different positive and negative coefficients in the objective function. Now both the dual simplex algorithm as such, as well as the example that we saw here where we solved problems with mixed type of constraints, we have illustrated, we have just tried to show that particularly in the second case, when you have problems with mixed constraint, where it is possible to solve using a judicious mix of simplex and dual simplex iterations, but then one has to be careful. If there is an optimum, we will definitely get it, but if the problem exhibits other things like unboundedness or infeasibility, then we need to carefully define the unboundedness and infeasibility rules for those situations. Here again we need to be a little careful to define the unboundedness and infeasibility, but the equivalent unboundedness rule actually represents infeasibility in the dual simplex iteration. Now let us spend a couple of minutes on understanding the simplex and dual simplex, the differences and so on. Now the regular problem that we have solved, a maximization problem which has all less than or equal to constraints and all greater than or equal to variables, is very ideal for a straight simplex application, because slack variables will qualify to be the basic variables. We can solve it entirely by the simplex algorithm. A minimization problem with all positive or non-negative coefficients in the objective with greater than or equal to constraints is a very ideal situation or ideal problem to use the dual simplex. If we have problems with a mixture of constraints and types of coefficients and so on, one would take the risk of solving it by judiciously applying simplex or dual simplex, or one would follow a very safe way of solving it only by simplex algorithm by adding artificial variables. Both simplex and dual simplex algorithms solve linear programming problems extremely efficiently. And we have also seen the relationships between the primal and dual, that one is a primal algorithm and the other is a dual algorithm, and so on. Now, the next thing that we have to see is, can we efficiently represent the simplex algorithm or the dual simplex algorithm. For example, if we have to write a computer program for the simplex algorithm, will we use the tabular form, or are there better ways of solving the simplex algorithm other than using the standard tabular form that we have seen? Now, that we will see in the next lecture.